For thousands of years, humans have looked up at the night sky and seen a tiny reddish dot. This dot was different from the stars. It wandered. It glowed with a steady, fiery light. The ancient Romans named it Mars after their god of war. Its color reminded them of blood and conflict. But today we see Mars not as a symbol of war, but as a symbol of hope. It represents a new frontier, a new beginning, and perhaps a new home for humanity. So what exactly is this grand concept of terraforming? The word itself gives us a clue. Terra is Latin for earth, and forming means to shape or create. So terraforming literally means earth shaping. Think of it like this. Imagine you find a beautiful but abandoned house. The foundation is good, but it's freezing cold. There's no air inside, and the garden is just barren dirt. You would need to install a heating system to warm the whole house. Terraforming is the same idea, but the house is a planet. Why would we even consider such an enormous, almost impossible undertaking? A single catastrophic event, like a giant asteroid impact, having a second self-sustaining home on Mars would be the ultimate insurance policy. However, we must also be clear-eyed about the sheer scale of the challenge. Its atmosphere is incredibly thin, about 100 times less dense than Earth's. Without a thick atmosphere or a global magnetic field, its surface is constantly bombarded with deadly cosmic and solar radiation. Imagine stepping onto the surface of Mars without a spacesuit. The atmosphere on Mars is a mere ghost of what we have on Earth. Standing on Mars would be like being at an altitude 3 times higher than the peak of Mount Everest. This leads to extreme temperature swings that are hard to comprehend. On a summer day at the Martian equator, temperatures might reach a pleasant 20 degrees Celsius. But on that very same night, they could plummet to a bone-chilling -73 degrees Celsius. Beyond the thin air and, the freezing temperatures, Mars has another invisible killer radiation. Mars, unfortunately, has lost most of both of these protective shields, leaving its surface dangerously exposed. Billions of years ago, Mars had a global magnetic field just like Earth's. But for reasons scientists are still debating, the planet's molten core cooled and solidified. Without this magnetic shield, the relentless solar wind began to strip away Mars's atmosphere over millions of years. Even if we could solve the atmosphere and radiation problems, we would still face the challenge of the Martian ground itself. Specifically, Martian soil is rich in perchlorates. These are salt compounds that are toxic to humans. Before we could start planting forests or farming crops on a terraformed Mars, we would need to deal with these toxic salts. Then there is the issue of water itself. We know there is a lot of water on Mars, but it is almost all frozen solid. As temperatures rise, the dry ice in the polar caps would sublimate first, thickening the atmosphere, which would then warm the planet further, eventually melting the water ice. The first, most crucial step in terraforming Mars is to turn up the heat. Luckily, we know exactly how a planet stays warm. It's all about the greenhouse effect. The southern polar cap, in particular, contains a huge amount of frozen carbon dioxide, also known as dry ice. The idea is to kickstart a runaway greenhouse effect. If we could warm the poles by just a few degrees, some of that dry ice would turn directly into gas, a process called sublimation. One of the simplest and perhaps most low-tech ideas for warming the Martian poles is surprisingly straightforward. Make them darker. Think about wearing a black shirt on a sunny day compared to a white one. The black shirt absorbs much more sunlight and gets hotter. One idea is to spread a thin layer of dark material over the vast expanses of dry ice. We could potentially gather dark-colored dust from other regions of Mars and transport it to the poles using fleets of automated rovers or rockets. If spreading dust on the surface seems too messy, how about we focus more sunlight onto the poles from space? The concept is to build one or more gigantic lightweight mirrors and place them in orbit around Mars. By concentrating sunlight onto the southern polar cap, we could deliver a steady stream of extra energy. To make a real difference, a soletta would need to be enormous, perhaps hundreds of kilometers in diameter. Instead, it would likely need to be manufactured in space, perhaps using materials mined from asteroids. Instead of relying on sunlight alone, what if we took a more direct industrial approach? This idea involves building factories on the surface of Mars that would produce and pump super greenhouse gases into the atmosphere. The plan would be to land automated self-replicating factories on Mars. These factories would be designed to live off the land. They would be powered by large solar arrays, or more likely, nuclear reactors that we would have to ship from Earth. While releasing Mars's own frozen carbon dioxide is a great start, it might not be enough to create the thick, warm atmosphere we need. The perfect candidate for this atmospheric import is ammonia, or NH3. Conveniently, many asteroids and comets in the outer solar system, particularly in the Kuiper belt beyond Neptune, are packed with frozen ammonia and water ice. These robotic shepherds would identify suitable ice-rich asteroids, attach engines to them, and then gently and precisely nudge them into a new orbit. As it blazes through the thin Martian air, it would heat up and explode, releasing enormous clouds of ammonia gas and water vapor. Instead of looking to the stars for new atmospheric gases, another audacious idea suggests we look deep beneath Mars's own surface. Mars is home to the largest volcanoes in the entire solar system, including the colossal Olympus Mons, which is nearly 3 times the height of Mount Everest. The most plausible method, though still far in the future, would involve drilling deep into the crust near a dormant volcano and detonating a series of powerful nuclear devices. The immense heat and force could theoretically melt the surrounding rock, creating a new magma chamber and triggering a massive eruption. All of these efforts to build a new atmosphere will be for nothing if we can't make it stick around. Mars lost its original atmosphere because its protective global magnetic field shut down billions of years ago. A much more plausible, though still incredibly advanced, idea is to build an artificial magnetosphere. This satellite would then generate a powerful magnetic field. The field would be large enough to encompass the entire planet, forming a magnetic bubble that would deflect the incoming solar wind, protecting the new atmosphere from being stripped away. Let's assume our grand engineering projects have worked. The orbital mirrors are shining, the factories are puffing out super greenhouse gases, and the atmosphere is slowly getting thicker and warmer. The first major consequence of this planetary warming will be the liberation of Mars's most precious resource, water. At first it will be a trickle, then a stream, then a torrent. Water will begin to flow across the rusty Martian terrain, carving new riverbeds and following the paths of ancient long dry river channels. Over decades and centuries, these flows will coalesce in the Great Northern Basin, a region called Vastitas Borealis. With a warmer atmosphere, liquid water, and a bit of protection from radiation, Mars is ready for its first inhabitants. So, the first wave of life we send to Mars will be the toughest, most resilient organisms we can find on Earth. Other types, like cyanobacteria, will perform the crucial task of photosynthesis. They will take in the abundant carbon dioxide from the new Martian atmosphere, use sunlight for energy, and release oxygen as a waste product. Alongside the bacteria, we will introduce another pioneer, lichens. Their fungal parts breaking down the rock while their algal partners photosynthesize, creating the first specks of green on the red landscape. Once the microbes and lichens have done their pioneering work, creating patches of primitive, nutrient-rich soil, Mars will be ready for the next wave of colonists, the first true plants. As they spread, they will form vast green carpets across the land, dramatically changing the planet's appearance and accelerating oxygen production. Finally, after many centuries, the soil might be deep and rich enough to support the first trees. Imagine the sight, the first forests taking root under the pale Martian sun, their dark green a stark contrast to the red rock. It would be a step-by-step assembly of an entire biosphere from scratch. After centuries, or maybe even millennia of dedicated effort, what would life on a terraformed Mars finally look like? The sky would not be the familiar deep blue of Earth. Because the new Martian atmosphere would still be thinner than our own and have a different composition, likely with more carbon dioxide, it would have a unique hue. And what an ocean it would be! The Great Northern Sea of Mars would be a vast, cold, and shallow body of water. The beaches would not be of fine white sand, but of reddish-black volcanic grit. The weather on this new Mars would be wild and unpredictable in its own way. Humanity would not be spread out evenly across the new Martian landscape. Martian architecture would be distinctive, designed to cope with the environment. Because of the lower gravity, which is only about 38% of Earth's, people would feel lighter and stronger. Outside the cities would lie the great Martian wilderness, the forests of hardy conifers and the plains of tough grasses, would be home to a carefully curated selection of animals. This new world would also be a scientific paradise. Living on Mars for generations would inevitably change not just our culture, but our very biology. The children born on Mars, who have never known Earth's heavy gravity, would grow up taller and more slender than their terrestrial ancestors. Their hearts and bones would not be strong enough to withstand Earth's crushing gravity, making them permanent residents of their new homeworld. Martian society would develop its own identity, shaped by the shared experience of living on a frontier world. The Martians, adapted to their world, and with their own unique culture, would eventually demand the right to determine their own destiny. The existence of a second thriving branch of humanity would mean that our species is no longer confined to one world. After exploring the spectacular and mind-bending technologies we might one day use to transform Mars, it is time for a dose of reality. The sheer scale of the project is almost beyond human comprehension. Even with the most optimistic scenarios and futuristic technologies, we are not talking about decades. We are talking about centuries and, more likely, millennia. The cost of terraforming Mars would be, without exaggeration, astronomical. It would require a coordinated and sustained global effort dwarfing any project in human history. In a world with pressing problems like climate change, poverty, and disease here on Earth, it is difficult to imagine humanity dedicating such vast wealth to a project on another world. Beyond the immense technical and economic hurdles lies a question that is perhaps even more difficult. Even if we could terraform Mars, should we? It is a pristine geological museum, holding secrets about the formation of our solar system and why planets like Earth become habitable while others do not. The most significant ethical concern centers on the potential for native Martian life. If there is life on Mars, no matter how small or simple, do we have the right to drive it to extinction? Many scientists argue that we should explore Mars thoroughly and exhaustively first, to be absolutely certain that it is a sterile, lifeless planet before we even consider changing it. So, if terraforming Mars is practically impossible with current technology, prohibitively expensive, and ethically questionable, why do we keep talking about it? The reason is that the value of the dream is not just in its potential completion. The dream of terraforming Mars serves a vital purpose right here and now. It is a powerful driver of innovation. The quest to terraform Mars, even if it remains a distant goal, acts as a powerful catalyst, inspiring a new generation of scientists and engineers to solve the hardest problems they can imagine. The red dot in our night sky is no longer a symbol of war, but a symbol of a potential future. It is a challenge, a promise, and a destination that will continue to fire our collective imagination, pushing us to be better, smarter, and more daring for many centuries to come.